Okay, so talking about volume today, talking about volume of prisms and cylinders. One of the things that I kind of like to view volume as, or maybe a way of thinking about how to create it, is kind of looking at like either like a textbook or a notepad or maybe a little block of post-it notes. And look at one of those post-it notes kind of on an individual basis. So let's say that I have a block of post-it notes that are the shape of this pentagon. Okay, we would agree that that one singular post-it note is probably pretty thin, right? Okay. Now, here's my thought: is that we want to make that infinitely thin. Okay, ultimately, so it has no width. Okay, because a post-it note or a piece of paper in front of you is still a prism. There's a length, there's a width, and there's a thickness to it. That thickness is just very, 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 very small, right? Does that kind of make sense? But if we kind of neglect that thickness and make it turn into ultimately no thickness, or let's instead just get our minds wrapped around it maybe a little bit better. Make it just a smidge thick. It's very so thin that you almost see through the paper, but it still has a thickness. Does that make sense? Okay. So if I take one of those pieces of paper, I could probably only just really easily find the area of it, right? But what if I take two of those pieces of paper, find their areas, and stack them on top of one another? And then find a third one's area and stack it on top of the first two. And keep doing that, and keep summing those areas together, and I keep stacking them on top of one another. Can you visualize that stacking them on one top of one another are going to create that block of post-it notes or that maybe notebook of paper? Does that kind of make sense? And if I add those individual areas up, okay, that should sum then to the volume of that prism. Okay? So, how does that help me maybe remember the formula for volume? Well, I'm finding that base area first, and then I'm going to multiply basically by how many of those things I can stack on top of one another, and that many, and I'm going to be able to stack on top of each other, is equivalent to the h, or the altitude of the prism. Does that make sense? Okay. So when we talk about volume, it's actually a very simple formula for prisms and cylinders, and the fact that it's just capital B times H, where capital B is the area of your base. So that might change depending on the polygon that is defined as our base. But then we just multiply that area by the altitude of the prism. Okay? H, make sure we understand, is the altitude of the prism. Okay? Capital B is the area of the base. By definition, volume is the space that an object occupies. Okay? Sometimes referred to as maybe the capacity of something. Okay? You guys go into restaurants and there'll always be a plaque on the wall that says that this has a capacity of 200 people, or it says a volume of 200 people. It means that that's all that place can hold, right? Okay. Same idea with volume. Volume is the amount of three-dimensional space that a object can hold or occupy. Is that okay with everybody? Pretty easy formula. Okay. Capital B times H. All right. When we talk about rectangular prisms, okay, you guys have dealt with these volumes before, and you simply just say volume is L times W times H. Have you seen that before? Well, L and W, what those are, if you remember back talking about rectangles and finding areas of rectangles, we said you can use L and W. We use B and H because that's what our textbook used, but you can use L and W. Is L times W the area of a rectangle? The area of maybe that bottom base, 24 by 20. If I multiply that by H, the altitude of my prism, it gets me my volume. Okay? The one thing I don't like about this formula is LWH is that it's only specific for rectangular prisms. Once you get to a trapezoidal prism, once you get to a maybe a rhomboidal prism or whatever, L and W are not there anymore because the bases are different. That make sense? Okay, so it might end up being, if it was a hexagon, that L and W disappear and get replaced with 1/2 AP. So those are things to kind of think about as we go through. That's one of the biggest mistakes I see people all the time do, is that they totally neglect what our bases are, and they always want to just say volume of any shape, any prism is LWH. It's just rectangular. Okay? But it does make things a little bit easier because we don't have to differentiate, what we're going to let our base be here. I can go 24 times 20 times 10, right? Okay. So maybe doing that, if that's L and W, I've said the bottom is my base, right? But because of the associative property, commutative property of multiplication, I could take 24 and 10, okay, 24 and 10, put those next to each other, and then that surface closest to us would be the base. Does that make sense? So it doesn't really matter. When I multiply that out, though, what do I end up with? 4,800. Okay? And it's going to be centimeters cubed. Okay? Because you have 3 linear dimensions here, right? This is centimeters to the first, centimeters to the first, centimeters to the first. And when we multiply like bases, we add exponents, right? So centimeters, 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 those are like bases. Exponents are 1 plus 1 plus 1 gives you 3. Okay? So that's cubic centimeters. Okay? There are some nice conversion facts that we need to know for things like cubic centimeters. You guys ever watch, your TV shows like, what's the one now? Like Grey's Anatomy, is that still on TV? Do people still watch that? When I was in high school, it was like ER. You guys ever watch that? Nothing beats ER. Gage, pay attention. Jump, man. You watch those shows and they say, like, give me 400 cc's stack, right? You know what cc stands for? Cubic centimeters. They're referring to some volume of something, okay? And that volume is in terms of cubic centimeters, okay? Does anybody know what 1 cubic centimeter is? What's another maybe conversion that we can use? You guys remember these things? Okay, these are unity blocks that you guys maybe dealt with in like 7th grade, 8th grade, whatever. Usually they came in like singular ones and then like rows of 10 or whatever. And they had rows or blocks of like 10 by 10. And then you had the big chunks, right? Okay. If I take and let each one of those side lengths be 1 centimeter, that would be 1 cubic centimeter. Does that make sense? Okay. That would be equivalent. 1 cubic centimeter is equivalent to 1 milliliter. Okay. That might be something you write down for just common knowledge throughout some of the stuff that we're going to do this week. 1 cubic centimeter. 1 cubic centimeter equals 1 cc equals 1 milliliter. Okay, they're all the same way of referring to something. If you've ever, anybody interested in like engines and stuff like that, like dirt bikes, or even if you go home and you look at your parents' mower or leaf blower, or, the engine will say something about cc's on it, and basically it's telling you the volume of gas that is able to be used inside those cylinders of that engine. Okay. So I am going to ask you, because I think it's important for you to be able to do this, to take things like cubic centimeters and change it into some other unit. Okay. So let's talk about how we would maybe change this into
let's just go cubic meters first. Okay. Change to cubic meters. And a lot of you are probably saying, well, I know how to do this because I've taken chemistry. So I know that King Henry died by drinking chocolate milk, right? Okay, where this is kilo. Is it hecta? This is deca. This is your base. So this is meters, liters, and grams. This is deci, centi, and milli. And that list goes on that way. This list goes on that way. Over here, you get things like micro and nano. Over here on this side, you get things like giga and tera and things like that. You guys have heard those things, right? You guys ever heard of gigabytes, terabytes? Okay, those are things over here. Heard of nanoseconds, things like that. They're to the right of milli, so they're smaller than milli. And that's something that you guys are accustomed to using. But I'm going to use this second, okay, in this conversion, because a lot of times with volume, people are going to misuse this. And I want you to make sure that you understand the procedure that allows us to use that the way we want to or that we need to. So right here, I'm going to actually do this the correct way, or the more direct way, I guess. Okay. When I take cubic centimeters, and I want to get to cubic meters, it's called dimensional analysis. And basically what we're doing is we're just using conversion facts. Okay. And one of those conversion facts is that we know that meters and centimeters directly relate to one another, right? How many centimeters are there in a meter? There's 100 centimeters for every 1 meter, right? Okay. Now, if I look at this, okay, remember what centimeters cubed means. It means centimeters times centimeters times centimeters, right? That's my units right now for that. When I cancel that unit there, because it's in the denominator, in one of these centimeters, I'd be left with 2 centimeters now, right? Centimeters squared. Does that make sense, everybody? So that tells me I need another one of these 1 meters over 100 centimeters. Because now those centimeters are going to cancel and now leave me with just centimeters to the first power. Is that okay with everybody? Telling me I need those to cancel as well. So I need one more conversion fact of 1 meter for every 100 centimeters. And now they cancel. Now all my units of centimeters have disappeared. Does that make sense, everybody? So whatever this was centimeters cubed. I need that many centimeters in the denominator. Okay? When I multiply that out, my numerator is going to give me meters times meters times meters, which gives me the units I was looking for, right? Up top, I'll have 4,800 times 1 times 1 times 1, which is 4,800. And now on the bottom, I'll have 100 times 100 times 100, which is a million, right? 6 zeros, correct? Okay. So I need to divide that 4,800 by a million, which tells me then, if I'm going to divide by a million, there's 6 zeros, correct? So it tells me that I need to move my decimal place from right there to the left 6 units. So it becomes 0.004800 cubic meters. Is that okay? Okay. Now, how does that relate to this? How can I get the same answer with this slider down here? Because you're accustomed to doing this by taking, we're in centi, so we're right here. Maybe you take your number that you're dealing with and you put it
underneath the unit that you currently have, and we want to go to base, we will go to meters, right? So we're going to hop over one space, two spaces, right? Well, if I do that here, does that give me the exact same answer as that if I just move it 2 decimal places? No. Because right there, this slider is for linear dimensions, okay? Or one-dimensional things. So really all I've done there, if I move that decimal place 1 spot to the left, it's really only changed that dimension to meters. Okay? Yes. So we need to change that one to meters. We also need to change that one to meters. So that one changing to meters says move it 2 more. Does that make sense? So 2 more for that second dimension. And then because this one needs to be changed to meters, we move it 2 more for that third dimension. So how many times did I move it? 1 spot, 2 spots, 3 spots, 4 spots, 5 spots, 6 spots, right? Does that equate then to that 1 million? Yes. Okay. So like Jordan was saying, because this is cubed, if you want to use the slider, by all means do it. Okay? But when you figure out how many spots you need to move, you then need to multiply that by whatever that exponent is. Does that make sense? Okay. If it was squared, I was converting a square area, then I would multiply that by 2 instead of 3. Is that all right with everybody? Because, and the reason for that, logic for that is because every single dimension needs to be converted. Okay. You might be a person that says, I don't like that. So the workaround is, well, if you don't like that, then just simply come up here and convert that one to meters right away, convert that one to meters right away, convert that one, and now can I multiply those out? And it will give me that. Okay? It'll be meters cubed as my solution. Is that something we can process and do?
What if my question was this? We've got volume is 4,800 cubic centimeters, but I want you to change that to liters. Okay.
Right now, when I think about centimeters all by itself, centimeters is just a distance, right? Liters is actually a volume. Okay? So I need to be able to kind of maybe deal with how I can look at this or visualize and think about this. And it all comes back to us being able to know that 1 cubic centimeter is equivalent to 1 cc, which is equivalent to 1 milliliter, right? So if I say I have 1 milliliter equal to 1 cubic centimeter, that right there says the exact same thing as that does. Is that all right, everybody? At some point, you might even see a question where I do all the work. I ask you to do all the work with centimeters, and then I ask you, okay, how many milliliters is this? It's a direct one-to-one relationship. Okay? But now if I've got it in milliliters, is it going to be easy to change to liters? Yeah. Oh, it's capital D. Okay, so if we're in milliliters, we're right here, right? I want to go to liters. Remember, your base is meters, grams, liters. So I go 1, 2, 3 spots. So 4.8 liters. Now, why did I only go 3 spots there? What's the unit right now in milliliters? Or what's the exponent? First power. So I can use that slider directly the way we normally do. Those are all little intricacies of paying attention to the exponents that you got to kind of learn by experience, learn by doing them, learn by maybe making mistakes every once in a while and then learning from those mistakes. What will happen if you don't pay attention to that exponent is that you'll have the same numbers. You'll have 4, 8, 0, 0, but your decimal point will be in the wrong location. Does that make sense? Okay.
So as we're going over homework questions and stuff like that, and you're getting the same numbers, just your decimal points in the wrong spot, always go back to this idea and say, I probably used this incorrectly. Okay. All right, so let's do this question. Take that and find the exact volume of the prism. So volume, I can't, and this is where people get in trouble. Can I use volume equals LWH right here? No, okay? Because L and W are the base area for a rectangle, and our bases are triangles. So I have to use volume is equal to B times H, where B then is 1/2 BH, correct? Now, when I look at my base, this is 8, right? That's 8, coming from those two things. What's this third side? 8 as well. You see how that's hidden on the other triangle? A lot of people will miss that and not pay attention to it. You can pull that over, put 8 there. Okay. Okay, so this is an equilateral triangle. So it tells me that there exists some line right here, my altitude, which is going to divide this 60-degree angle up here to a 30-degree angle, right? 30, 90, 60. You know, this breaks down to 4, doesn't it? There we go. Monday. All right, so 60. So that's my inside. So what's H going to be? 4 radical 3, right? So now I got enough stuff to go over here and go 1/2 base of 8 times altitude of a 4 radical 3. That's going to multiply together, give me 16 radical 3. Okay? And that's an area, so it'd be square units. Okay? I'm going to multiply that by my altitude here in a moment. But before I do that, does anybody remember maybe an easier way of doing this question? This area? What kind of triangle is that? Equilateral. Do we remember that equilateral triangles have that formula? S squared would be 64, right? What's 64 divided by 4? 16. Is that a little bit quicker? And that's the benefit of knowing more formulas, is that when you are presented with a shape that maybe it's an elongated process, maybe another formula can shorten that for you. So now, capital B, 16 radical 3, and it would be inches squared. And then we'll multiply that by H. What's H for your prism? 10. And that would be inches to the first. Inches squared times inches to the first gives me inches cubed, right?
Why are you allowed to combine the radical 3?
Say again?
Why are you allowed to combine the radical 3 and 10?
I'm just multiplying that number there by 10. Because what it's saying is I have 16 radical 3 times 10. So it really means, times 10 is repetitive addition, right?
Oh, okay.
So I'd have those 6, in all the 10 of those, I'd take a 16 out of all of them. And I'd have radical 3 plus radical 3 plus radical 3, whatever. The best thing to do is take a radical 3 out. Take that radical 3 out, and you get 10 16s in here, so that's 100. But that is going to be inches cubed, right? What if I wanted to go to feet? What if I want to go to feet cubed? 160. And this is when we're in the English system. Okay. We don't have a slider. Okay. The slider, King Henry died by drinking chocolate milk. That thing is nice because all powers of 10. Okay. Inches to feet, feet to miles, that kind of stuff. There are no common bases. So we have to be able to use this concept to get into feet cubed if I'm in the English system. Okay, so there's really no way around not learning this. Does that make sense to everybody? Okay. If I've got inches cubed up here, I need inches on the bottom, right?
and I need feet to show up on top. So I always go through and do my units first. If the units aren't right, it doesn't really matter what the numbers are. Okay, units are as important, if not more important, than my numbers. So cancel those out. Okay. Now I'm going to make the relationship. How many feet and inches? 1 foot for 12 inches, right? So I'm actually going to take 160 radical 3 and divide it by
12 times 12 times 12, and it turns into 1728. And now it would give me how many cubic feet I have. Does that make sense? And you can put that as, I don't care right now, you can put that as a decimal or whatever. But I want you to see that, obviously, when we talk about linear dimensions, everybody knows 1 foot, 12 inches. 12 inches, 1 foot, right? But when I ask when I'm in square feet or cubic feet, change that into cubic inches or square inches, a lot of people just want to use that factor of 12 one time. Say divide or multiply by 12. Hopefully you're seeing there that we don't do that. If I want to go into from square inches to square feet, I divide, instead of by 12, I divide by 144. Okay? So every 1 square inch, let's write this one. For every 144 square inches, that makes up 1 square foot. Does that make sense? Okay. For every 1,728 cubic inches, that makes up 1 cubic foot. Okay. And those are things. Those are known facts. Okay. But they're not things that people memorize. Does that make sense? Because it's just going to clutter your knowledge about maybe conversions that you need to memorize. Okay. Because they're not as easy to recognize as these. Does that make sense, everyone? Okay. For instance, maybe knowing that 2.54 centimeters equals 1 inch. Okay, that's something we have to memorize. It's a known fact, but we can't go through any math other than putting a centimeter and an inch right next to each other and comparing them to get that conversion. Does that make sense? Where these 1 to 1728 or 1728 to 1 are things that you could develop without memorization. All right, so let's talk about how and we did this a couple days ago, so I'm not going to bring up the GeoGebra again, but as I take a prism and I start changing that base and start adding more and more and more sides, that base slowly turns into a cylinder, right? Okay. So if the volume of a prism is B times H, then the volume of a cylinder is the exact same thing. Okay. Nowhere is this ever said in a textbook or anything like that, but you can view cylinders as kind of a special case type of prism. Okay. Because we treat them the exact same way. It's just special because definition of a prism is that the bases are polygons, well, a circle is not a polygon. So it doesn't really classify as a prism, so we need its own vocabulary word, but we can do all our work as if it is a prism. Okay. Now, that being said, you can use B times H, but because capital B in a prism is evolving and changing from question to question, one question might be a triangle, next one might be a square, one might be a hexagon. For any question that deals with the volume of a cylinder, what is the base always going to be? Yeah, it's always going to be pi r squared because the base is always a circle. So pi r squared h a lot of times is the formula that you get for volume of a cylinder. Okay, but that kind of the derivation of that, the creation of that is the same idea as being able to stack a bunch of those circles pi r squared on top of one another, and then adding all those up, which is essentially multiplying by h. Yes. So on this question on the bottom, it is indeed 72 pi cubic centimeters. Okay. Because volume is, again, pi r squared h. So you got pi r is 3. So square that, times it by an h, which is 8. So you get 72 pi centimeters cubed. Okay. Because when we found this here, that was centimeters times centimeters, right? So that's centimeters squared and times the altitude of another centimeter, so centimeters cubed. The question somebody had last class was, what if I want to convert that to
milliliters, okay? Or not millimeters, okay? We know we should move the decimal place how many spots? One spot. In which direction? To the right, okay? This is the way you want to think about this. 72 pi means 72 times pi, right? Both of those have a decimal in them. 72's decimal is right there. Pi's decimal, if I write it out, obviously is 3.14, whatever, right? All you have to do is move one of those decimals one spot to the right, okay? You're not going to move both of them. Which one would make more sense for you to move? Yeah, the 72 one, right? Okay? Because when you move it, it's just going to create the introduction of a 0 in there somewhere, right? Okay? Where if I move the one in here, first I got to write that number out. It messes up pi and all that kind of stuff because of rounding. So it's better to move that one. So I'm going to move that one to the right 1 unit. So it gives me 720. And this is still times pi then. So 720 pi millimeters cubed would be the same thing. Okay? Those are the same quantities, right? Okay, so if Cameron has 72 cubic centimeters, 72 pi cubic centimeters in front of him, and Gage has 720 pi cubic millimeters in front of him, they both have the same amount of volume. Okay? It's being described different. Some questions that you're seeing in your homework are like these, okay? Where they're going to ask you to chunk things up like we do a surface area, right? So procedurally, it's the same idea. If I chunk these things up, over here, you see that cutting down there, I would get this prism, right? Okay. Now, the dimensions of that prism come from the fact that if that's 24, doesn't that have to be 24? And then what would that distance right there have to be then? It'd be 12. So you're seeing over here where that 12 comes from.
Why is the 24 large then?
Huh?
Absolutely, why is the 24 large then?
Because that distance right there, that altitude, is that 24. Okay. So we can chunk it up. Can we find the volume of this thing by saying the volume of that by going L times W times H? That'd be the volume of that, right? Would the volume of this thing over here be pi r squared times H divided by 2, because it's only half the cylinder, right? Evaluate both those and then do what with those two individual volumes?
Add them together.
Add them together.
So could you just technically do half pi large squared?
Yes. Yes. All right, so those are the types of problems that Math Excel has, and they're not that great. So I'm going to give you something like this. Okay? And this is where the worksheet kind of comes into play. Just trying to compensate for their lack of good problems. It says a full waterbed mattress is 7 feet by 4 feet by 1 foot. It says if water weighs 62.4 pounds per cubic foot, what is the weight of the water in the mattress to the nearest pound? Meaning that if I had in front of me like a plexiglass aquarium that was 1 foot by 1 foot by 1 foot, okay, and I neglect the weight of the plexiglass, but I fill that thing with water, it's going to weigh 62.4 pounds. Okay? We want to know basically how many of those would fit inside this mattress. Okay? How many of those would fit inside this mattress? Now we can chunk them up and all that kind of stuff to fit into the dimensions of the mattress. But am I basically talking about a volume of a mattress that is LWH, which is 7 foot by 4 foot by 1 foot? Is my mattress 28 cubic feet? Okay. Now let's say that I'm, last class we said we put this mattress on like a second floor or third floor like loft, okay, that we built or we're constructing. Would we want to make sure that our construction
is going to support a certain weight. So wouldn't it be nice to know how much weight's going to be up there before people get up there? Okay, so, and this is what engineers do a lot of times. It's called statics and talk about forces and stuff like that. But we're going to try to figure out if our structure would be able to hold this weight. Okay, well, it's 28 cubic feet, but 28 cubic feet using this conversion rate right there. That's and this is where people struggle. 62.4 pounds for every, now it doesn't have a number with the cubic feet, right? It's 1 cubic feet, or foot, however you want to say that. Okay? Is that all right with everybody? Whenever they have a rate written like that, it's basically 62.4 pounds per 1 cubic foot. Because of the 1, they never write it any differently than this. Can I multiply those out? Would that tell me then the weight of that mattress full of water? Say again? Okay. Something like that. Okay. What were you saying, Sabrina? Yes. Okay. Now here's the thing. If you get in the mindset of doing it every time, I could have written that it's 1 cubic foot for every 62.4 pounds, and then people aren't sure, do I multiply, do I divide, those types of things. So if we set it up like this where we get our units to cancel, we'll always get the right operation, multiplication, or division. I want to do, I think I got one more here. Okay, it just talks about Olympic-sized swimming pool, and we want to find out how many gallons this thing holds. Okay, so it's just if you know anything about swimming pools, an Olympic-sized swimming pool is just a prism, correct? No shallow end. Any swimmers in here? No shallow end, no deep end. It's all the same thing. Okay. So if I find the volume of this prism, it'd be 164 times 82 times 6.6, right? Okay. So that would be volume is. Say it again. 7,576.8. Okay, so that's cubic feet. All right. This says change this thing into gallons. So it says feet cubed, right? So when I multiply, where do feet cubed need to go? Bottom. Because they need to cancel, right? That's where because they need to cancel, that's telling me where they need to go. And now there's a direct link between gallons and cubic feet, right? So what number needs to go here? 7.48, right? Multiply that out. Yeah. 6,674.46. Hold on a second. 164 times 0.6 times 82, right? Okay, so you told me this number wrong. That number is 88756.8. Then we'll multiply that by 7.48. And that's how many gallons that is. Okay. Yeah. 88756. Those red calculators are sticky. So then multiplying that by 7.48 gets you that number there. Okay. So that's 663,900.864 gallons. Okay. Now, why would I want to know how many gallons are in my swimming pool? Okay, so if I want to fill it up, let's say that it's empty, and I want to put a hose into it, and I know that my hose has a certain rate of flow that is maybe 10 gallons per minute. Can I figure out how many minutes that would take?
Yes.
Yeah,
Divided by
okay.
that.
How can I figure out how many, like when I have a garden hose at home, how can I figure out its flow rate?
You say I guess you can you put it in like a giant thing. That's
Take a 5-gallon bucket, right? Or a 50-gallon trash can, or whatever. Some capacity, some object that you know its volume based off of its manufacturing, right? Okay. And you turn your hose on and you hit start on a stopwatch at the same time, right? Once that fills up, you click stop, right? And now you know how fast it takes to fill 5 gallons up. So can I use that as a conversion rate?
Yep.
And then you can tell me then how fast I can fill up 663,000 gallons. Is that all right, everybody?
Yep.
Those are the types of questions that you're going to see on that worksheet. Okay? Those are the types of questions that I'm going to ask to see if you understand what's going on Tuesday's test. Okay? There will be some of those initial, easy, boring ones, but there will also be some of these that make you think. Okay? Authentic type problems, real life problems that at some point in your life you're going to have to be able to do. See you tomorrow. Have a good day. Thank you too.